Are we alone in the universe? Scientists, philosophers, ethicists, cavemen, and women have pondered this for millennia. Back in the 1960s, we started SETI, the search for extraterrestrial intelligence, and there was great optimism that within a few decades we would have unambiguous evidence of intelligent life. But the radios have been silent. There's been no "Hello, Earthlings" call from the cosmos. However, life doesn't need to be technological for us to detect it, and today I want to take you on a journey of how we're pushing the boundaries of technology in order to actively pursue the answer to this question. I would like to start with an image taken by Voyager. Voyager is the farthest probe we have sent into space, and just after it had crossed the orbit of Pluto, it turned back and snapped this picture in 1990. That's it. That's us. All of Earth reduced to 1 pixel, Carl Sagan's famous pale blue dot. I just love this image. It provides us a glimpse as to what our planet would look like to an alien astronomer. And she could tell that life was on our planet, because in Earth's reflected light, she would see signatures of oxygen and methane. These gases are produced by microbial life and wouldn't exist together in combination around a lifeless world. This is because without a constant and high flux of both gases from biology, oxygen and oxidizing gas would quickly destroy methane, a reducing gas. Geology alone won't produce high concentrations of these gases in a Sun-Earth analog. Thus, it is the combination of an oxidizing and a reducing gas together that constitute a strong biosignature or an indicator of life. And it's our best hope for finding life outside our solar system. The idea that we could do this for planets around other stars fascinates me, and so in my research, I model how these biosignatures change depending on the host star's temperature. We know what Earth looks like around our sun, but what would it look like around another star? Stars come in many sizes, with larger stars being hotter and smaller stars being cooler. Around a larger star, there is more high-energy UV radiation, and this high-energy light breaks apart, destroying some biomolecules like methane. But the same high-energy light fosters the reactions that form others, such as ozone. And ozone is used as a proxy for oxygen since it's easier to detect. The second step of what I do is to simulate what we would then see from Earth with a telescope. This step is important since just because some biosignatures are more abundant in an atmosphere does not mean they are easier to detect. To give you an idea of what we're hoping to see for other terrestrial planets around other stars, here are the spectra for 3 planets in our own solar system that have very different signatures: Earth, Venus, and Mars. I want you to think of a spectrum as basically a light fingerprint. And just as fingerprints are unique to each human, light interacts in very predictable ways with the molecules in an atmosphere, creating its own molecular fingerprint. But trying to detect the light from these planets is no easy feat. A star outshines its planet by over a factor of 1 billion. That means for every billion photons we get from the star, we get just 1 from an Earth-like planet. It's a bit like trying to find a firefly while staring directly into a spotlight. It seems to be an impossible task. And imagine that that spotlight is in California and you're observing from Massachusetts. That's what we're trying to do. Remarkably, though, astronomers are near to doing just that. And in the next decade, we're building some of the largest telescopes so far that should have the capacity to detect biosignatures around the closest planets outside of our solar system. And that's where my thesis of modeling the detectability of these biosignatures fits in. When building a multi-billion-dollar telescope, it's vital to ensure that we're looking at the correct wavelengths or colors of light, that we're observing long enough to gather as much light as possible, and at high enough resolution to tease out these spectral fingerprints. What drives me every day is the prospect that in our lifetimes, we will be able to have signs of life on another planet. The universe is incredibly vast. We expect there to be 40 billion Earth-like planets in our galaxy alone. And there are billions and billions of galaxies. However, so far we have only one example of a planet with life so far. Ultimately, we want to discover, is life a cosmic imperative, popping up on every habitable planet in the universe, or is it exceedingly rare, arising only under the strictest of conditions? We just don't know. But for the first time in human history, we have the scientific capability to start to answer this question. And either answer will have far-reaching consequences in our society, from philosophy to science. Are we the last generation of lonely Earthlings? I hope so. Thank you.